All right, welcome to the second video for our ecology model. In this video, we're going to continue with our population discussion, and we're going to talk about population growth and population regulation. Now, with population growth, right, we're interested in knowing how the species numbers are changing in the population over time. Okay. So in order to kind of estimate how populations are changing over time, we can use two models to describe their rate of change and the change in the size of those populations. The first model is exponential growth, and then the second model is logistic growth. And we'll go into detail about what these two models are. First, let's think about, why do we need to model population growth? Why do we need to understand these changes? So first, maybe we want to just describe changes occurring in a population, right? So we can understand how that population is changing just a little bit better. And if we understand how a population changes currently, we can use that to determine how that population is going to change in the future, which is super important if you're trying to conserve a species and you're trying to maintain a specific population size. So if you can model and predict current populations really well, and your modeled data will match the actual observed data, then you're confident in your numbers that you can predict into the future. And so then you can determine management strategies. You can determine, again, how many individuals you can harvest from a population for resources, whether it's trees or animals or fish, right, to use for resources. And so understanding those population dynamics is really important if you're when you're looking at species populations. And so the exponential growth equation, or the growth model, is a model where we're looking at kind of no constraints on that population. Um, and the individuals in this population are reproducing continuously. Their generations are overlapping, and the population is changing in size by this specific proportion every instance in time. And so every point on this curve is an instance in time that we can calculate, right? And when the conditions for that population are favorable, so like when they have good environmental conditions, when they have a lot of resources, when there's no competition, right? When each individual can get enough energy and enough resources to survive and reproduce with no constraints, then you get this exponential growth curve, this J-shaped curve here, right? And so this is basically saying that population size increases exponentially over time, and you get this really rapid increase in population growth. Now we can model exponential growth by taking your population growth rate, which is R, and this is just the rate of change in a population at each instant in time, and you multiply that rate of change by the number of individuals. And so that will tell you your population growth at each time step. Okay. And the way you calculate your exponential population growth rate is just by subtracting the death rate from your birth rate. Okay. So if you have 100 individuals every year that are born, 80 individuals die, then your population has a growth rate of 20, right? So your population growth rate is increasing. Now, R tells us a lot of things, right? So based off of this relationship, this birth rate minus death rate, if R is equal to 0, then your births are equal to your deaths and you have no growth, right? If R is less than 0, then your population is decreasing. The way R becomes less than 0 is if you have more deaths than you do births. So say you have 120 deaths and 100 births, you are now at a negative 20, so your population's decreasing. Same thing with increasing population, right? but instead then you have more births than you do deaths, right? So 120 births, 100 deaths, you have 20 new individuals added every generation. Okay, and so this is the formula for that exponential growth, right? So again, exponential growth is assuming there is no constraints, everything's fine all the time, and individuals are successful, they get energy, they're able to reproduce with no kind of effects. Okay. However, we know that this ideal scenario is not the case at all in natural populations. And in natural populations, those favorable conditions can and do exist, but they don't exist forever. They don't continue indefinitely. So that means that a population will experience exponential growth, but eventually that exponential growth will cease and it will be capped by some sort of limitation. And that cap is what we call a carrying capacity. And we denote that by K, the variable K in our model. And what carrying capacity basically says is this is the maximum population size that can be supported indefinitely by the environment. So the resources that the environment has can support this many individuals without overusing those resources, right? And the growth rate will decrease as a population nears carrying capacity because your resources are beginning to run low. And as your resources start to run low, your death rates, your mortality rates become higher and your birth rates become lower. Okay. And what we expect is once that population, right, so it grows exponentially, reaches carrying capacity, and then so your R is very high down here, so lots of births, low deaths. But then as it gets closer to carrying capacity here is about 450, 460 individuals. Your R becomes low because now your death rate is more than your birth rate, or it's starting to equalize, right? So let's say initially you have 60 births and 20 deaths every generation. Maybe up here you now have 60 births and 50 deaths every generation. But at carrying capacity, that birth and death rate theoretically should equal 0. So now you would be at 60-60. So that population size is not changing, and it will kind of fluctuate around that carrying capacity. This model, this figure curve is a logistic growth curve. Okay, so populations increase rapidly, then they stabilize around that carrying capacity. Each population has its own individual carrying capacity that's based on what the environment can hold, right? So the amount of resources that are in that area. So the carrying capacity of, say, squirrels in one area may be different for that same species in another area, just based off of environmental differences and resource availability. Now, this logistical growth equation is just a modification of the exponential equation. So remember, R and times N is that exponential growth equation. All we're doing is we're saying, okay, let's modify this exponential growth based off of a carrying capacity. Okay. So essentially, your change in population size is based off of the number of individuals you have, their growth rate, and the carrying capacity. Okay. The higher the number is, the closer it gets to K. So the less individuals that you add to that population. So the lower R is, the closer to 0, I should say the closer to 0 R becomes. Okay. Now, a way we can visualize this is, let's say you have, for example, 20 individuals, right? 20, and the population can hold 100. 100, right? Divided by 20. Okay. Now let's say we have a growth rate of like 0.10 or something, right? Now I'm not really going to do the the formula here, but what you can see though is that this is going to lead to a growth, right? This is going to add individuals, right? So 10% of 20 is 2. So just based off of this exponential form, you're going to get 2 individuals added every year, right? Now, this carrying capacity says, okay, we're going to modify that curve based off of how close this population is to the carrying capacity. If it's far away from the carrying capacity, you actually get a value, right? So you get 20 over 100 is what? 0.5, not 0.5, but 0.20, which is obvious, right? And so 1 minus 20 is 0.8. Okay, so now you're multiplying 2 times 0.8, right? And so that will give you, let's go ahead and do that. I'm bad at math. Let me get my calculator out real quick. So, right, 0.2 times 0.8 is 0.16. Okay, and so you're adding, 0.16 individuals. So let me just make this a little clearer for you all. Let me actually do something real quick. Here we go. All right, so let's do this here. Here we go. So let's say we got 0.10. We said we were at 20 for N. We were at 100 for K. Let's just do the math. Let's go ahead. So 0.10 times 20, right? And we said that 20 over 100 is 0.2. 1 minus 0.2 gives you 0.80, right? So if you do that math, you get 0.10 times 20 times 0.8, right? So that's 1.6 individuals added every year. Now, as this number increases, right? So let's say after 10 years, right, we've got 16 individuals added, right? So now that number is 36. This is going to make that ratio higher and closer to 1. Whenever it becomes 100 over 100, you get 1 minus 1, and that equals 0. So when this term becomes 0, 0 minus whatever this, or 0 times whatever this is 0. So now all of a sudden you're adding 0 individuals to that population, right? So if this is 0, that makes this term 0, and so this is 0. So you're adding no individuals, and that's what you get here, right? So this K is taking this exponential growth equation and turning it into this logistical equation based off of carrying capacity. Now, with this logistic growth, we're assuming a lot of things. First, we're assuming that you have equal access to resources for all species, for all individuals in that population. You have equal survival rates, and that the carrying capacity is not changing. And so in this example, we're assuming that 7,500 is the carrying capacity regardless of all environmental situations, right? However, in the real world, we do know that there is competition, especially intra-specific competition, which is where you just have competition between members of the same species, or members of the same species. So for example, this individual here, I think it's a seal, you have individuals of that same species competing for the same resources. So that's what intra-specific competition is. So whenever you see a INTRA specific, that's same species. Now inter, INTER specific, is between species, right? And so that would be like between the seal and maybe a otter, right? That's interspecific. But we know that intraspecific competition does exist, and we see it. And so that means that as populations increase in number, the intraspecific competition increases because you have a higher density and you're affecting the amount of resources that's available in that location. So that competition becomes stronger. And so then what we see is that the carrying capacity could actually vary annually. And your carrying capacity will vary based off of environmental conditions, right? And we actually have that interspecific here. So interspecific is competition with other species for resources. Now, some other factors that kind of caused this population at carrying capacity to vary are things like density independent factors and density dependent factors. Okay, so population growth regulation, right, can really be influenced not only by competition but density based factors as well. Density independent factors are factors that affect the birth and death rates of the population, but they are independent of the actual density within the population, and so the number of individuals in the population, right? So an example of this is weather conditions, catastrophes, natural disasters, those types of variables that affect the species numbers. And so, for example, areas that have less temperature, or I'm sorry, years, okay, so years that have more precipitation can lead to higher population sizes, and years that have less precipitation can lead to lower population sizes, right? And so those increases and decreases in population size then aren't determined by the density of the population themselves, so the initial density, right? So you don't get an increase because your density was low, or you don't get a decrease because your density was high. You basically get an increase in density whenever you have quote unquote good years and bad years in terms of weather conditions, right? And so those changes in population size are really independent from the initial density of the population. And so there was this insect that was studied in the 40s, and they found that their populations fluctuated with temperature and rainfall. And so you can see that there's a lot of variation from year to year, and it has to do with like wetter years, cooler years, hotter years, drier years, right? So I think like the higher populations are when it's wet and more rain, and lower years are kind of when it's dry. And so it's really not based off of the density of the population at all. Now, with density dependent factors, that's basically the opposite. So density dependent factors actually changes the birth and death rates and dispersal rates as the density of the population changes. So as density increases, your birth rates and your death rates will your birth rates will go down, your death rates go up, and then organisms leaving, so immigration is leaving the population, will increase. And so your population will decrease in size. So if you have lower birth rates, higher death rates, and then also a large number of individuals leaving the population, then your population will start to fall back down. Now, as the population falls back down, your birth rates will go up, death rates will go down, and immigration will go down. So now all of a sudden your population starts to go back up. But then when it gets at a high density again, your birth rates will decrease, death rates will increase, immigration increases, and your population goes back down. And so you can get these population fluctuations that regulate the population kind of around an average carrying capacity based off of those density dependent factors. So the following images, so this figure here is showing what kind of population relationship. So is it density dependent or density independent? And so just pause the video, take a minute, think about that. And so hopefully you said this is density independent. And so the population growth rate does not change as a function of density. So as density increases, population growth rate remains the same as if density was lower. However, this figure shows a relationship between population density and population growth rate. So this is density dependent. So when you have a low population size, you have a higher growth rate. And when you have a higher population density, you have a lower growth rate. And again, that's due to various factors that are affecting changes in birth rate, death rate, immigration rates as population density increases or decreases. Now, one of the last things we're going to talk about in this section is the life history characteristics that organisms can express and show towards, or they can express and show in their basically daily lives. So species can be what's called a R strategist or a K strategist, and basically they can undergo R selection or K selection. And these are the extreme ends of a reproductive spectrum, right? So let's say we have life history strategies that go along this gradient. R strategists are on one end and K strategists are on the other. Now, R selection is referring to the R variable that was in the population growth model, so that intrinsic rate of increase. K selection is referring to K in the carrying capacity of a population. So R selection related to that intrinsic rate of increase is selection for high population growth rates. K selection, they have low population growth rates. And so their populations are seen as having growth rates that are similar to growth rates that are near or at carrying capacity, right? Whereas R selection has really high population growth rates. Now, looking at the traits that are observed in these different species that express these different types of reproductive strategies, if we look at an R selected individual or species, they're basically living fast and dying young. And so they have really short lifespans, have really rapid development, so they tend to mature early on, so like within their first year of life, etc. They have very low parental investment, so that means they don't have a lot of parental care for their offspring. They have high reproductive rates, so maybe they have a lot of offspring at one time, or they reproduce several times during the year. And so they're producing a lot of offspring very quickly. So that takes a lot of energy. So that means they have low energy or low time to actually take care of the thousands of offspring or hundreds of offspring that they're producing. And an advantage of a species having this type of lifestyle is that they can take advantage of newly disturbed habitats or uncrowded habitats. So they can go in and take over those habitats relatively quickly. Whereas if you had, say, one offspring per year and it took a long time to become mature, you can't take advantage of those undisturbed habitats relatively quickly. And so most insects, small vertebrates, so like mice, weedy plant species, some fish species, they represent kind of that R-selected life history strategy. Now, K-selected is the complete opposite. So K-selected is basically this slow and steady lifestyle where the species are long-lived, they develop relatively slowly, They have later maturation rates. They invest a lot of parental care in their offspring, and they have low reproductive rates. So they may only have 1 to 2 offspring over their lifespan. Um, and so some examples of these are like large mammals, humans, for example, reptiles such as tortoises and crocodiles, long-lived plants. And so these plants take a long time, animals take a long time to become mature. Maybe it's not after age 3, 4, sometimes like 10 in terms of like your larger mammals, or 8 or 10 or so in terms of years. And the advantage is that in crowded conditions where there's resource limitation and competition, they can be really efficient at reproduction because they're providing parental care, because they're putting a lot of energy into making sure their offspring is successful and is able to make it to a reproductive age, so that that organism can continue to reproduce from generation to generation. So very different strategies in terms of these K and R selected species. And so just like I mentioned, these are the extremes of this reproductive continuum. And so not all animals, not all organisms will fall as an R strategist or a K strategist, right? So they can fall like anywhere along this gradient. They can be maybe more so towards an R strategist, but maybe they have like 1 or 2 K strategist characteristics, or vice versa. Maybe they're more like a K strategist, but they have like a couple of R strategist characteristics. And so a lot of organisms actually fall along somewhere in this gradient and not necessarily at the extremes. And so it's important to just kind of remember and make that distinction. Okay. And so that's it for this second video in our ecological or ecology module. With the next video, and we will look at, so with our next video, we'll look at community ecology. We'll talk about what community ecology is, and we'll look at some very important terms and ideas related to this aspect of community ecology. And so with that, we'll see you in the next video.